In this chapter, you will find out that there's very much similarities between chapter 9 and 10 and 3 and 4 in earlier this semester. So if we start with the fact that we're given a function for the angle theta as a function of time, and this angle is given as 2.0 radians per second cubed times t cubed, then knowing a specific time will allow us to find the angle. So for part A, we're going to substitute to find theta 1. We're going to substitute 2 seconds in for t. So this is 2.0 radians per second cubed times 2 seconds cubed. And this gives us 16 radians. And then if we want to change this to angles, we take 16 radians times 180 degrees for every pi radians, or 360 degrees for 2 pi radians, or whichever conversion factor you're more comfortable with. And you'll notice that the radians will cancel, leaving us with degrees, and we get about 920 degrees. The second time we're given is for t equals 5. So we again plug in 5 for t, and we get 5 seconds cubed. This will give us 250 radians. Once again, if we take 250 radians multiplied by 180 degrees for every pi radians, we get about 14,000 degrees. Moving on to part B. Part B, we have an interval of time. So the angular displacement from t1 to t2 is delta theta, which is theta final minus theta initial. In the previous chapter, chapter 3, we used delta x equals x final minus x initial, but now we're talking about angles, so we will keep them in terms of radians. The final angle was 250 radians minus 16 radians, and we get 234 radians. If we wanted to find this in meters, the arc length, if you remember from your trig, is r times theta. So we have an r times theta final minus an r times theta initial, which is the same as saying r times delta theta, right? So this is going to be 0.18 meters is the radius times 234 radians. And you'll find out that whenever you have a unit of length and radians, that unit of length will always take over and the radians will disappear. So now we have an answer for part B. Moving on to part C. If we wanted to find the angular velocity average, similar to what we did before, it's theta final minus theta initial over t final minus t initial. We used this previously as x final minus x initial over t final minus t initial, so it's displacement over time, 250 radians. minus 16 radians over 5.0 seconds minus 2.0 seconds. And this gives us about 78 radians per second. Keeping in mind significant figures, of course, right? And if we want to change this to revolutions, what we can say is that this is the same as 78 radians per second times 1 revolution is 2 pi radians, and 1 minute is 60 seconds. And if we look at what cancels, we have the radians that cancel out, we have the seconds that cancel out, and we have revolutions per minute, and this gives us 740 revolutions per minute, which a lot of times we write as RPMs, right? Revolutions per minute, or RPMs. The next part asks for instantaneous angular velocity, and that, from what we know before, is the derivative of the displacement. So this is going to give us the derivative of the theta function, which is 2.0 radians per second cubed times t cubed. And notice that only the t is a variable here. So this is going to give us 3 times the 2 will give us 6.0 radians per second cubed times t squared, right? And now if we plug in the values that they want, this is, the first one is evaluated at 2 seconds, so this would be 6.0 radians per second cubed times 2 seconds squared. That will give us 24 radians per second. Notice that the units work out beautifully. The second one is 6.0 radians per second cubed times 5 seconds quantity squared, and that gives us 150 radians per second. Moving on to the next part, we're asked to find the instantaneous acceleration. So this is part E. The acceleration is given by the symbol alpha, and the average is omega 2 minus omega 1 over t2 minus t1. So this is the same as delta v over delta t when we did linear acceleration. So we have 150 radians per second minus 24 radians per second all over 5.0 seconds minus 2.0 seconds. You get radians per second or radians per second squared, and you get 42 radians per second squared. Last part, if we know what the function for the angular velocity is, then the angular acceleration is the derivative of the angular velocity. So that's the derivative with respect to time of the function for the angular velocity omega, which is 2.0 radians per second cubed. 6.0 radians per second cubed times t squared. again, t being the only variable here, so this gives us 12 radians per second cubed times t. And lastly, if we want to find the value of the instantaneous acceleration at a specific point, we plug in the time for that specific point. So if we plug in 2 seconds here, we get 24 radians per second squared. And if we plug in the second time period of 5 seconds, we get 60 radians per second. So hopefully you see similarities between these equations and what we've done previously for linear motion.